Welcome to Module 1 of our course on electrical machines. In this module, we will focus on two of the most important types of machines in electrical engineering, transformers and direct current (DC) machines. These machines are fundamental to power systems, industrial applications, transportation, and everyday electrical devices. An electrical machine is a device that converts electrical energy to mechanical energy to electrical energy, or modifies the form of electrical energy without changing it to another type of energy. For example, a generator converts mechanical energy into electrical energy. A motor converts electrical energy into mechanical energy. A transformer changes the voltage and current levels of an alternating current (AC) supply without converting it into mechanical form. Understanding these machines requires knowledge of both their operating principles and practical construction details. 1. Transformers. 1.1 Operating Principle. The transformer is a static electrical machine that transfers electrical power from one circuit to another at the same frequency, but usually at a different voltage level. It operates based on the principle of electromagnetic induction, which states that a changing magnetic flux in one coil induces an electromotive force, EMF, in another coil that is magnetically linked. In its simplest form, a transformer consists of a primary winding, connected to the input power source. A secondary winding, connected to the load. A magnetic core that provides a path for the magnetic flux. When an alternating voltage is applied to the primary winding, it creates an alternating magnetic flux in the core. This changing flux induces a voltage in the secondary winding proportional to the turns ratio of the transformer. 1.2 Classification of transformers. Transformers can be classified in several ways. A. Based on function. Step-up transformer increases voltage from primary to secondary. Step-down transformer decreases voltage from primary to secondary. Isolation transformer, same number of turns on both windings, used for isolation without voltage change. B. Based on construction. Core type, windings are placed around the laminated core limbs. Shell type, core surrounds the windings on three sides. C. Based on supply. Single-phase transformers. Three-phase transformers. D. Based on application. Power transformers. Distribution transformers. Instrument transformers. Auto transformers. 1.3 Construction. A transformer's main parts are core, made of laminated silicon steel sheets to minimize eddy current losses. Windings, made of copper or aluminum conductors, insulated for safe operation. Insulation, oil, paper, varnish, or synthetic materials to separate windings. Cooling system, natural air cooling, oil cooling, or forced cooling systems. Conservator tank in oil-filled transformers, for accommodating expansion of oil. Bushings, insulated entry points for high-voltage connections. 1.4 EMF equation of a transformer. The induced EMF in a winding is proportional to the rate of change of magnetic flux linkage. In verbal form, the equation is induced EMF equals 4.44 times frequency times number of turns times maximum flux in the core. This relationship applies to both primary and secondary windings, with the turns ratio determining the voltage transformation. 1.5 Phasor diagrams. In operation, transformers have primary current, secondary current, and magnetic flux that are phase-shifted with respect to each other. The phasor diagram graphically shows these relationships, allowing engineers to visualize load effects, voltage drops, and magnetizing current requirements. 1.6 Equivalent circuit model. The transformer's electrical performance can be represented by an equivalent circuit consisting of series resistance, representing copper losses. Series reactance, representing leakage flux. Parallel branch for core losses and magnetizing reactance. This model is essential for performance analysis under load. 1.7 Losses in a transformer. Transformers experience two main types of losses. Core losses, caused by hysteresis and eddy currents in the core material. Copper losses, caused by resistance in the windings. Minimizing these losses improves efficiency, which for large power transformers can exceed 98%. 1.8 Voltage regulation. Voltage regulation measures how much the secondary voltage changes between no load and full load conditions. Good regulation means the voltage stays nearly constant under varying load. 1.9 Frequency response. The transformer's performance varies with frequency. At very high frequencies, leakage inductance and capacitance can cause significant distortion, while at low frequencies, magnetic saturation becomes a problem. 1.10 Special types. Polarity test determines winding orientation. Autotransformers, a single winding serves both primary and secondary, smaller size and higher efficiency. Three-phase transformer connections, star, delta, and combinations for system compatibility. Impedance matching, for efficient power transfer between circuits. Isolation transformers, for electrical safety. Instrument transformers, potential transformers, PT, and current transformers, CT, for measurement and protection. 2. DC machines. 2.1 Operating principle. DC machines operate on the principle that a current-carrying conductor in a magnetic field experiences a mechanical force, motor action. A conductor moving in a magnetic field induces an EMF, generator action. Thus, the same machine can work as either a generator or a motor depending on the energy flow. 2.2 Construction. The main components of a DC machine are yoke, the outer frame providing mechanical support and magnetic path. Poles, generate magnetic flux. Armature, rotating part containing conductors. Commutator, mechanical rectifier that converts AC in armature to DC output. Brushes, carbon or graphite contacts that transfer current between stationary and rotating parts. 2.3 Types of excitation. DC machines are classified based on field winding connection. Separately excited. Shunt wound. Series wound. Compound wound, short shunt and long shunt. 2.4 EMF and torque equations. The generated EMF depends on the flux per pole, the total conductors, the armature rotation speed, and the number of parallel paths. Similarly, torque is proportional to armature current and magnetic flux. 2.5 Power stages and efficiency. The mechanical and electrical losses in a DC machine, including copper loss, iron loss, and friction, determine overall efficiency. 2.6 Armature reaction and commutation. Armature reaction distorts the main flux, affecting performance. Commutation is the process of reversing current direction in armature conductors to maintain unidirectional torque or voltage. 2.7 Characteristics and applications. DC generators, used for excitation systems, battery charging, and special applications. DC motors, used in traction, cranes, and variable speed drives. 2.8 Starting and speed control. DC motors require starting resistors to limit inrush current. Speed can be controlled by varying armature voltage, adjusting field current, changing armature circuit resistance. 2.9 Electric braking. Includes plug-in, reversing supply polarity. Dynamic braking, connecting motor to a resistor. Regenerative braking, returning power to the supply. 2.10 Design of DC machines. Design involves output equations for sizing, selection of main dimensions, armature winding design, commutator and brush design, field system layout, interpole design for improved commutation.